Building a house out of glass might sound strange, but with fiberglass rebar, it's entirely possible. Far from being fragile, these bars are strong enough to support the weight of massive bridges and towering skyscrapers. Every year, millions of tons of this new material are produced, opening up fresh possibilities for modern construction. But here's the big question. How can strands of glass as thin as a human hair be turned into solid bars? Just a quarter the weight of steel, yet tough enough to last for decades. Up next, let's follow the journey from tiny grains of sand to one of the 21st century's most promising building materials. Fiberglass rebar is actually made from two main components: glass fibers drawn from silica sand and epoxy polymer resin that binds and reinforces them. This combination creates a material that doesn't rust and can sit in seawater for up to 50 years without losing strength, while regular steel can start corroding after just a few months. And alongside the fiberglass rebar process, the next part of the video reveals the incredible journey of steel rebar production waiting for you. Back to fiberglass rebar. It weighs only 1/4 as much as steel, reducing thousands of tons of load in large structures. Yet its tensile strength is about twice that of standard carbon steel. In terms of cost, the upfront price is typically 20 to 30% higher than steel, but its much longer lifespan brings the overall lifetime cost of a project down. Fiberglass rebar is mainly made from glass fibers, and as we know, glass fibers come from silica. Many people confuse sand with silica, but in reality, only very pure sand deposits, with silica content as high as 99%, can meet the strict standards of the glass and construction materials industry. This high-grade quartz sand doesn't come from beaches or deserts. It's extracted from massive open-pit mines. In these mines, quartz rock layers are so dense and tightly bonded that ordinary machinery can't break them apart. That's why engineers have to use industrial explosives in a carefully calculated process, drilling deep holes into the rock, placing the right amount of explosives, and detonating them in controlled sequences to reduce vibrations and control the size of the fragments. Once the blast goes off, the massive rock formations split into smaller pieces. Massive excavators quickly scoop up the broken rock and load it onto heavy-duty trucks. From there, the raw material is hauled to the primary crushing facility. At this stage, powerful industrial mills run non-stop, breaking down the solid rock into uniform grains of fine sand. This finely processed silica sand becomes the essential foundation, marking the very beginning of the entire fiberglass production process. Although the sand has already been crushed, it still hasn't reached the purity required for fiberglass production. That's why the material is sent into a modern washing system, capable of processing up to 220 tons of sand per hour. The process begins as heavy trucks unload the crushed material into a massive hopper, which directs the sand into a regulated flow system for cleaning. The first checkpoint is a primary screening system equipped with precision meshes, such as 30 mesh screens, meaning 30 holes per square inch, to filter out oversized particles. Only the finest sand grains, meeting the required specifications, move forward into powerful agitation chambers, where they are thoroughly cleaned with high-pressure, needle-like water jets. After nearly 15 minutes of continuous agitation, the sand-water mixture begins its controlled descent into a spiral separation system. Here, centrifugal force comes into play, pushing heavier metallic particles outward and gradually filtering them out. The remaining stream, now lighter and more refined, continues on to a mechanical separator designed to remove any last traces of iron. Once the sand is dried, it is packed into 50-pound bags and transported to the fiberglass manufacturing plant. This is the largest fiberglass manufacturing plant in the United States, producing more than 500 tons of fiberglass every week. After obtaining purified silica from mining, it is transported to the plant's storage facilities. The first step is to mix the raw material with about 15% sodium carbonate and 10% calcium carbonate, combined with 70 to 75% silica to form the initial batch mixture. This ratio helps lower the melting point of silica while also enhancing the durability of the finished fiberglass. When all the raw materials are ready, they are poured into a filtration system to remove any final impurities before entering the main production process. After filtration, the materials are carried by a system of conveyor belts to the mixing area. These conveyors can move hundreds of tons of sand per hour, running continuously without interruption. In the mixing zone, the batch is fed into high-speed stirrers, where each grain is evenly blended and subjected to a deep, continuous, and rigorous cleaning process. This step ensures that even the tiniest impurities still clinging to the surface of the silica grains are completely removed, allowing the raw material to reach maximum purity. The mixture is then directed into a massive gas furnace, where temperatures can soar to 1,650 degrees Celsius, hotter than the raging lava erupting from an active volcano. Technicians closely monitor the process and pour the mixture into specialized crucibles. Once the temperature and composition are stabilized, the crucibles are sealed to maintain the extreme heat and carefully control the melting process. Inside the production area, workers wear fireproof suits and Kevlar gloves to withstand the intense surrounding heat. After about 24 hours, the raw sand has completely transformed, turning into a glowing liquid that flows like lava. The bright mass at the bottom of the furnace is molten glass, a dense, viscous material that has reached the ideal temperature and consistency. For several more hours, the glass remains in its molten state, allowing any trapped gases to escape, resulting in a final material of the highest purity. And this is the special step that creates the shape of the fiberglass. From the main tank, the molten glass flows down into a special unit called the bushing. Its base is made of platinum alloy, drilled with thousands of microscopic holes. These holes determine both the number and the diameter of the fibers being formed. The entire process is carried out under strict conditions to avoid any contamination. As the molten glass flows through the tiny holes, gravity and mechanical pulling transform it into filaments as thin as a strand of hair. Each measures only about 5 to 25 microns in diameter, much thinner than human hair, yet incredibly strong. Thousands of fibers are drawn simultaneously, forming a glowing stream under the intense heat. One fascinating aspect of the entire plant is that it must run continuously, 365 days a year, because if it stops, the fibers solidify into a hardened mass that can damage the equipment. Right after the fiber drawing stage, skilled workers gather thousands of ultra-thin glass filaments into larger strands for easier handling. At the same time, high-pressure nozzles spray cool water to instantly chill the fibers and prevent them from snapping under the intense heat. As a result, each bundle of fiberglass achieves the stability and quality needed for the next steps. The fiberglass strands are then wound into large coils known as rovings. This process is fully automated, ensuring consistent tension and uniform length. The result is neat, durable rolls that serve as an intermediate product for making fiberglass rebar and other composite materials. After the fiberglass rovings are produced, they are fed into the fiber assembly line, where they are suspended and spread into parallel bundles. Each strand is only a fraction the thickness of human hair, yet when combined they form a steady and reliable stream of material for the next stage. This arrangement not only keeps the process running smoothly, but also ensures consistency in the raw input. It serves as the foundation for the entire fiberglass rebar manufacturing process. The fibers are guided into a polymer resin bath, which can be either epoxy or recycled PET resin. The system keeps the glass fibers under precise tension, ensuring they stay straight and evenly aligned before entering the bath. This controlled tension prevents slack or breakage during processing. The resin penetrates deep into each strand, both protecting the surface and bonding them tightly together. This step transforms loose glass fibers into a unified mass, ready to be shaped. The degree of resin penetration directly determines the strength and lifespan of the finished rebar. The resin infused into the glass fibers can come in many different colors, ranging from bright green to milky white. After resin impregnation, the fiber bundles are pulled through a long circular die. The pulling force keeps the fibers evenly stretched, while the die compresses them into the shape of a reinforcing bar. This step gives the product its form, turning thousands of fine strands into a solid, continuous piece. It's also where the surface ribs are initially formed, helping the rebar grip concrete more effectively. Next, the bars move into a curing oven, where heat hardens the polymer completely. High temperatures lock the glass fibers inside a rigid matrix, creating a durable structure. The surface ribs are preserved in their exact shape, ensuring strong adhesion once placed in concrete. Immediately, the still-hot composite bars pass through a system of high-pressure water jets. The cooling water instantly stabilizes the dimensions and prevents the resin from deforming while it's still soft. The jets also wash away excess resin and fine glass dust from the surface. Thanks to this step, the rebars enter the curing stage in a clean, uniform condition. After curing, each bar is inspected for quality and cut to the lengths required by customers. Industrial cutters guarantee clean, sharp cuts without damaging the surface. Finally, the finished rebars are packaged and stacked neatly for storage and transport. From delicate glass fibers to robust reinforcement bars, the transformation is complete, ready to replace steel in modern construction. Fiberglass rebar is an alternative to traditional steel rebar and serves as a core component in construction used to reinforce concrete, which is naturally brittle and prone to cracking. In home building, fiberglass rebar is placed inside concrete structures such as foundations, columns, and beams. It forms a strong supporting framework, giving concrete, which is only strong in compression, the added ability to resist tension. This makes houses stronger, safer, and more durable over time. So, you've just seen the entire journey of fiberglass rebar production. Pretty impressive, right? But alongside it, steel remains the most widely used reinforcing material in construction, with a manufacturing process that's just as fascinating. Steel is made from iron, so the first step is mining iron ore. Massive open-pit mines are dug to extract iron-rich ore, which is then transported by heavy-duty trucks to processing facilities. There, the ore is crushed, screened, and cleaned to remove impurities and increase its iron content. The result is refined ore, ready to be fed into blast furnaces for the next stage of steel production. Once the iron ore has been ground into a fine powder, the journey of purification begins. The mixture is blended with water into a thick slurry and directed into massive flotation cells. Here, the key lies in flotation reagents, surface active chemicals added with precise control. These agents render the iron-bearing particles hydrophobic, while silica, clay, and other impurities remain hydrophilic. As compressed air is continuously pumped from the bottom, millions of microscopic bubbles rise, attaching themselves to the chemically tagged iron particles. The ore gathers into clusters, forming a thick, reddish-gray froth that floats to the surface. Meanwhile, the worthless gangue sinks steadily to the bottom, completely separated from the valuable material. This iron-rich froth is carefully skimmed off and collected through multiple cycles, producing a concentrate with Fe content often exceeding 65–67%, more than twice that of the raw ore. It marks a critical turning point where unshaped stone is reborn as a refined resource, fully prepared for the demanding path of metallurgy ahead. After obtaining the concentrated ore from the flotation tanks, the next stage is filtration and dewatering. The iron-rich slurry is fed into vacuum filtration systems, typically drum or disc filters. Under the pull of pressure differentials, water is drawn out, while the fine ore particles remain, forming a moist filter cake on the surface. This step significantly reduces the moisture content, ensuring the material is better prepared for the pelletizing and subsequent firing processes that follow, allowing them to proceed with greater efficiency. From the filtration tanks, the iron concentrate emerges as a fine, dry powder, red as dust. But in this loose form, it is far too fragile to be fed into a furnace. To solve this, the powder is mixed with a measured amount of water and binding agents, then poured onto giant rotating discs tilted at an angle. With each steady turn, the tiny grains begin to roll and cling together, growing in size, rounding out, and transforming into small pellets with a distinct reddish-brown hue. By the time they leave the discs, the formless powder has become millions of fresh pellets, uniform and spherical, yet still soft and delicate. These young pellets must endure further stages ahead to gain the strength and hardness required to withstand the fiery heart of steelmaking. From the great conveyor, the glowing red pellets continue their journey into the rotary kiln, a colossal steel cylinder stretching dozens of meters, set at a slight incline and turning slowly on its axis. Inside, flames shoot from the kiln's mouth, sweeping the entire length and turning the chamber into a blazing river of heat. As the drum rotates, the pellets tumble and roll evenly through temperatures ranging from 1,200 to 1,350 degrees. This constant motion ensures each pellet is baked uniformly from core to surface, eliminating weak spots or cracks. Impurities and residual dust are burned away, while the ore particles fuse together into a dense, solid structure. By the time they reach the kiln's end, the once fragile spheres have hardened into resilient pellets, clad in a tough shell and ready to move onward into the cooling stage. Once the iron ore has been pelletized or sintered, it joins forces with the blazing hot coke fresh from the ovens, all converging at the top of the blast furnace, the beating heart of iron making. Inside these towering structures, layers of ore, coke, and limestone are charged in sequence, meeting a powerful blast of hot air injected from the base. At temperatures soaring above 2,000 degrees Celsius, the coke ignites fiercely, releasing carbon monoxide that strips oxygen from the ore, reducing it into streams of molten iron glowing red-hot. Yet alongside this fiery transformation comes a staggering cost. Massive volumes of CO2, fine dust, and noxious gases escape from the furnace, making this core step of steel production one of the largest single sources of industrial pollution on the planet. Once it leaves the blast furnace, the molten iron, still blazing red-hot, is transferred straight into the basic oxygen furnace, a colossal steel vessel lined with refractory bricks. Here, the raw metal undergoes a violent purification. From above, a massive lance descends, blasting a jet of pure oxygen at tremendous speed onto the liquid surface. The oxygen ignites instantly, stripping away carbon and impurities, sending pillars of flame and bursts of smoke high from the furnace mouth. Amid the roar and blinding sparks, every fraction of carbon is burned off, transforming brittle pig iron into steel, cleaner, tougher, and infinitely more versatile. It is the very moment of rebirth when crude metal evolves into the foundation of human civilization. But steel cannot remain in its molten state. Immediately, it is channeled into continuous casting machines. Streams of liquid steel pour into water-cooled molds, solidifying into billets, slabs, or blooms. This marks the first tangible form of steel. From these semi-finished shapes, the journey of transformation continues. Reheated and sent through colossal rolling mills, the steel passes under rollers weighing dozens of tons. Thick slabs are stretched into thin sheets. Blooms are drawn into massive coils, and square billets become long, slender bars. With every roll and every press, the metal moves closer to its destiny, rising as the skeleton of a skyscraper, spanning the length of a bridge, or forming the frame of an automobile. From the searing oxygen furnace to the thunderous cadence of the rolling mills, the entire process is a symphony of metal. The moment when steel is born, clad in the form the world has been waiting for. Before leaving the mill, steel must undergo one final trial by fire, a rigorous round of testing to prove its worth. Each batch is subjected to strict inspection, stretched to measure tensile strength, compressed to gauge its load-bearing capacity. Once it clears inspection, the steel is cut, bundled, and packaged with precision. Coils are tightly bound with special steel straps. Rebar and beams are stacked, secured, and labeled with their grade, dimensions, and production batch. For export, many products are wrapped in protective coatings to guard against moisture and rust during long voyages. At last, everything is ready to be loaded onto trucks, trains, or ships, setting out from the factory toward construction sites. So there you have it, two amazing manufacturing processes. Fiberglass rebar and steel rebar are made in very different ways, yet both give strength to the world we build. Fiberglass offers lightness and durability, while steel provides the backbone of our cities. Together, they show the balance between innovation and tradition. If this journey inspired you, leave a comment, like, and subscribe to the Factoran for more stories of the world's strongest materials.